So after discussing these columns and also the detectors, it's time now to see that why and how the interpretation of chromatogram occurs and what are the factors actually. So we will be studying these interpretations one by one. So the correct interpretation actually is very important because it gives you the qualitative and quantitative analysis about the qualitative idea that how many different analytes or how many different components are present in that particular vaporized sample, and it also gives you that how much amount each sample has, that each vaporized sample has in that particular mixture. So if you have done certain issues, then what happens that if you have, then it lead to false identification, wrong quantification, and that result will be in a compromised state. For example, if you are checking the drug purity, or if you are doing some environmental monitoring, then it becomes important to give you to analyze your sample with high specificity. And we have seen that detectors, certain detectors are so specific that they gives you information about the presence of a particular volatile component at the level of 10 raised to the power minus 13 or sometimes 10 raised to the minus 15 gram. So that is very important. That is very high selectivity, very high selectivity. So sometimes what happens that you see that the chromatogram is coming out perfect, but a simple drift in the baseline or simple occurrence of some unaccounted peak can make your whole experiment infectious. So you have to be very cautious while checking the drug purity, and you have to check the different peaks that are in conformity with the number of analytes present. Similarly, what actually a chromatogram is? So on the x-axis in the chromatogram, it is actually a pictorial representation. So on the x-axis you have always retention time, that is retention time here. Retention times you always have, that is you represent by TR. Similarly, the detector response is always like this on the y-axis, detector response. So ideally speaking, you have a very good baseline, and ideally speaking, you must have a peak for the mobile phase, then you have good peak for each of your component, volatile component. So the features are baseline, you should have a very smooth baseline, retention time, the peak widths, here the peak widths, similarly the peak heights, peak height and the peak area, that is the area this peak. Because the peak height, that is called as this peak height, and the peak width, sometimes it is called as peak width, is sometimes it is called as W. Sometimes we take half of W. So these factors are very important, because we have also seen while we were working with elution chromatography that these are the terms which actually we use while predicting the efficiency of any column in advance. So the retention time, reproducibility, it should be plus minus 0.01 minute. Otherwise, if it is greater than that, then the results are not very good. They are not very precise, you can say. So we have to check that our reproducibility will be good, and it should be, the range should be plus minus 0.1. So a chromatogram gives you a qualitative picture and the quantitative picture of the different analytes present in your sample. Okay. So you look for baseline, you look for retention times, you look for peak width, and you look for peak height and the peak area. Now what you have to keep in mind that you always, if your peak is like this, now you can see that there is a too much peak width. So you have to be cautious that this type of peaks is not advisable. It's not ideal peak. Similarly, if your peaks are coming very close, then it's a problem of optimization. Your peaks must be well separated and they must be sharp. Okay, so and the retention times is not too much. For example, if you have like this, if you have one peak is coming and after a certain time, after maybe 2 hours, then you have to do certain optimizations. For example, you can do temperature programming then. So you have to look for the retention times. Retention times not between the two components should not be too much, or it should not be very close. Otherwise, what happens, that superimposition, or you can say that peak overlapping occurs. So if the retention times are too close for the components, then overlapping occurs, and at the same time, if the retention times are too great, then it means that your peaks are very far apart. So you have to look for those situations. Similarly, retention time, that is, it is actually the time from injection to peak maximum. It actually, retention times tells you about the interaction of the analyte with the stationary phase, and it is also relates the volatility. In GC we have seen it, that your stationary phase should be very less volatile as compared to your analyte, as compared to your sample mixture. Similarly, your stationary phase should have 100-degree more boiling point as compared to the boiling point of the components, of the maximum boiling point of any of the component. So you have to look for retention time because it reflects about the stationary or about the stability. Similarly, if you have short TR, then it actually implies a weak interaction. We have already discussed all these features while we were discussing about the elution chromatography. Similarly, long TR means it is going to stay for longer times. Short TR means fast elution, and long TR means late elution. Because you can see that now your analyte has a strong interaction with the stationary phase. So high boiling compounds or give you actually the strong interaction. In the column temperature increases or shifts the TR. It is actually the TR. It is simply this. R must be a subscript here. So you have to look for this. So TR actually gives you a lot of information about the probable, you can say about the probable working or about the probable ideality of your separation. The peak area is actually directly proportional to the concentration, and the detector must have a linear response. For example, we have seen that some detectors have response up to 10 to the power 5 times. So the detector must have a good response, and the peak area is actually proportional to the concentration of the analyte. Similarly, integration methods, we can have a number of methods, that is the trapezoid method, the tangent skim method, and the valley drop method. Similarly, we have certain internal standard methods for which actually corrects for the injection variability. Now, for example, in FID, response is proportional to the number of carbon atoms. Okay, because that actually combustion of the carbon, the combustion of your sample which contains carbon is directly proportional to the ions produced. In spite of carbon, you have some other heteroatoms like chlorine, oxygen, or nitrogen, or sulfur. Then that response is not proportional. That is, the response will be, in that case, the response would be weak as compared to the carbon. So carbon has a 1:1 response, but the other heteroatoms does not have that 1:1 response. That is, they have a weak response. Okay. So peak height versus peak area. The peak height actually gives you an idea about the fast screen, that whether all peaks have similar width or not. And peak area is more reliable because it accounts for the peak broadening, and it also gives you about the quantity of that particular analyte. So the important thing is that you have to use area upon height ratio to detect the column overloading, that whether your column is overloaded or not. So we have to follow certain guidelines. So the mandated is that the peak area must be less than 2%. So this is the importance of the peak height versus the peak area. Similarly, the peak shape. We have already discussed that the ideal peak shape should be Gaussian. It is not like this, or it is not like this, or it is not like this, single point coming like this. It implies that there is no interaction with the stationary phase. Your analyte is not interacting here. Similarly, this fronting and tailing must be avoided. So an ideal peak must be sharp. It's a bell-shaped curve. So this type of peak is not advisable, this is not advisable, and of course this is not advisable. So the tailing factor, this is the expression for tailing factor. So for an ideal tail, this must be, tailing factor must be close to 1. But if it is greater than 1.2, then it implies a tailing, that is, it is tailing like this. Just like the resolution, which we have seen that it must be greater than or equal to 1.5. So these are the factors which tell you about the ideality of your ideality of your separation. Now what are the causes? This is actually caused by the active sites, column contamination, and the wrong injection of the solvent. Suppose that you injected your solvent and it does not vaporize. So it gives you, it gives you some peaks which are not ideal. That peak is not Gaussian. Similarly, if there are traces of water, then it causes irreversible tailing. So you have to make sure that your carrier gas is pure enough and there is no adsorption in your column. So you have to look all these factors, because all these factors actually give rise to change in the peak shape from the ideality, that is your peak will no more be Gaussian. Similarly, baseline behavior. A good baseline should be flat and stable. It is not like this. This is not an ideal baseline. An ideal baseline is like this. So what changes the baseline? The drift, that is the detector, change in detector temperature, or the fluctuations occurs because of change in the velocity of the mobile phase, the change in the velocity of the carrier gas. That is, your column pump is not properly working. It implies that your rotors are not working. Similarly, noise should be avoided. It may be electronic or it may be electrical, any issue. Similarly, ghost peaks are there, and ghost peaks are because of the contamination. The most important aspect of getting ghost peak is because of the contamination. Similarly, we have to check for the septum bleed. We have to check that your columns, the stationary phase packed columns, are working fine. That is, temperature is not too high. Otherwise, if temperature is too high, then the stationary phase will also start eluting with your sample. So you have to check for the bleed of the septum, bleed of the column as well, so that you can avoid the ghost peaks or unidentified peaks or unclaimed peaks. That is, unclaimed peaks or unidentified peaks because of the column bleed. So you have to check all these things. Similarly, resolution. That is the most important aspect. So we have already discussed this. Resolution may be defined as, for a two-component system, twice of TR2 minus TR1 upon W1 plus W2. We have already discussed for a two-component system. For a two-component system, component 1 and component 2. Okay. So baseline separation should be there, and resolution should always be greater than 1.5. We have already discussed a lot on this. So if it is less than that, then we get overlapping peaks. We get like peaks like this. And in this case, since we get an overlapping peak, so you cannot quantify, because the area, the common area comes into play. So you cannot quantify. Quantify becomes unreliable. You cannot quantify them because there will be some common areas which we have seen. Because if you extrapolate it, and if you extrapolate it, then this becomes the common area where you are going to add this area. That is the shaded area. Similarly, we need optimization. So optimization is done with regard to column length. That is, we have to change the column length, keeping in mind that if the column is too long, then the runtime will be increased. So you have to optimize the column length. That you have to optimize the length of the column. You have to optimize the stationary phase selectivity. You have to select the stationary phase with regard to the old rule, like dissolves like, or like prefers like. That is, for non-polar, you have to have non-polar. Similarly, for a polar phase, you must have a polar and a light. So you have to decide in terms of that. Similarly, you have to have a good temperature control. That is, your oven must be in a very isothermal condition at a constant temperature. So a slight change in carrier gas flow, because that is HETP. Remember that is A plus B upon U plus Cu. So Cu, again, that is the carrier velocity. That is very important. A small change can drastically change the resolution. So you have to look for the length of the column. Okay. So it should be kept as long as possible, provided that the retention times not increases too much, because the moment you increase the length, the height equivalent to the number of theoretical plates increases, and the number of theoretical plate increases, then resolution increases. But at the same time, the time of run also increases. So you have to keep in mind about the time also. Sometimes you can do temperature programming, sometimes you do certain solvent programming, and we have discussed all these aspects in our previous unit, that is unit 3 of this advanced analytical technique course. Okay, so you have to check for this important factor, that is resolution must be, RS value must be, that RS actually must be greater than 1.5 in any case. Okay, so there are certain peak problems, that is broad peaks implies that poor injection problems, there may be certain leaks or there may be some dead volume. Okay. Similarly, if we have a double peak or splitted peaks like this, then it implies that there are certain injection issues. We have to change the injection port. For example, if we are using a split one, then we can go for a splitless one. Similarly, if your sample was in liquid state and you are getting a double peak or a splitted peak, then there are chances that your sample does not get completely vaporized. That is, you have incomplete vaporization of a sample. Your sample actually did not get fully vaporized. Similarly, a peak fronting, actually a long fronting of the front part of your peak, Gaussian peak, implies that your column is overloaded. You actually overloaded too much of your sample. Similarly, a peak tailing implies that adsorption occurs. That is, the solute get adsorbed on the stationary phase. So that leads to peak tailing. That is peak tailing. Now, if you want to draw, this is the fronting part, and this is the tailing part. This is the fronting part of peak, and this is the tailing part. Now you can see that your peak is very much widened, it is very much broad. So ideally your peak must be like this. That is, it must not be broad. So peak fronting occurs because of the column overloading, and the tailing occurs because of the adsorption on the stationary phase. Similarly, you have to check for the ghost peaks, and it actually poses the quality check risks. So you have to be very sure that all the peaks belong to all the components. There must not be some additional peaks, and moreover there must not be some missing peaks for any analyte. Okay, so the column overloading. Column overloading occurs when more sample is actually introduced more than the limit of the stationary phase. So stationary phase can handle only, for example, 5 microliters of sample, and you have introduced 10 microliter, for example, in certain cases. Then of course, if the column gets overloaded, then the resolution, then the actual efficiency will be compromised. So you have to check for the column overloading. Similarly, you have to check for the asymmetric peaks and for the poor resolution. That is whether you are getting this type of result or you are getting this type of result. So you have to check for that what is happening. So there may be some quantitative error, that response is not linear, or calibration curve is not good, or reproducibility is not coming. In one case you are getting 3 peaks, but after 5 runs you are getting 4 peaks. So you have to check for all these systems. Similarly, this generally occurs because your sample is actually concentrated. So how you can resolve these issues? You can resolve these issues by taking lower concentration, by diluting your samples, by using the split injection technique, or the using split injection ports. Okay, and in those split injection port, you have to take a smaller volume. You have to take a smaller volume just to avoid the column overloading. Okay, so you have to keep in all these things in mind so that you can effectively work with your GC and you can get the best resolved peaks, so that you can have a very effective separation of your vaporized sample. Okay, so thank you with this, and we'll be covering the other parts in the coming slide.